Hello everyone. In the previous lesson, we talked about continuity at a point. We said that continuity or to be continuous at a point requires three things: the function being defined, limits exists, and the value of the function to be equal to the value of the limit. If those three conditions are met, that means the function is continuous at that point. If not, the function is discontinuous. We check these conditions on graph, and we studied how graphs look like if the functions are discontinuous. In this lesson, we will do the same for the functions algebraically. So, the new things that we are going to study in this lesson is learning two types of discontinuity. Discontinuity fall into two categories: removable and non-removable discontinuity. Let's talk about each one by one. If discontinuity is non-removable, then limit does not exist, like having a jump, having a break. If limit does not exist, we can't remove the discontinuity. It is called non-removable discontinuity. On the other hand, if limit exists, then we have removable discontinuity, which means there's just a hole. So by removing discontinuity, we just fill that hole. So what makes this function discontinuous? This disconnection. If I remove this disconnection, if I connect those two parts of the graph, I would make the function continuous, right? So all I'm going to do is filling this gap. Similarly, I have a gap, a point here, and I have a solid dot here. And when I put this point back on top of the um, empty point here, then I could make this function continuous, right? Without an interruption, smoothly going graph. So my aim is removing this discontinuity by filling the gap, So we can do that only if we have a hole. Otherwise, when we have a jump or when we have a break, we can't do that. We can't mm, connect those two parts of the graphs. We cannot connect those two parts of the graphs. There is no way. But we can connect these two parts, just filling the gap. We can connect those two parts, just putting this point back on this empty circle. So by making this point filled so that it will be an uninterrupted graph. So that's what we are going to do in this lesson. We will check whether the function is continuous or not by checking those three conditions. If the function is discontinuous, we will determine what kind of discontinuity we have. If it is removable, we will redefine the function by filling the gap and see what happens. So how do you redefine the function if the function is removable, the discontinuity is removable? So it's pretty simple. We are going to write a piecewise function for this situation. So we will have two conditions: x equals to the value given and x is not equal to the given value. For x is not equal to the given value, we are going to write the given original function. For equal, we are going to write the value of the limit. Remember, if the function is continuous, the value of the limit is same as the value of the function. Normally, I'm supposed to write the value of the function at equal condition, right? So since for continuous functions, value of the limit is same as the value of the function, then I'm going to write the value of the limit instead, because I'm going to fill this gap, or I'm going to put this point back here. So by using this rule, we are going to redefine our function. So let's take a look at the questions. Discuss the continuity of each function. Determine the point of discontinuity if it exists. If the function is not continuous at x equals c, specify whether the discontinuous is removable or not. If removable, write newly defined function to make it continuous. So before we begin, You need to know how to find point of discontinuity. For piecewise functions, we check the conditions of continuity. Those three conditions: function being equal to, function is being defined, limit exists, and value of the function equals to the value of the limit. Those three conditions should check for piecewise functions. For the others, we are just going to check the anti-domain. The anti-domains will be the points of discontinuities. Alright, let's get started. First question, x plus 1. What are the points of discontinuities? So, first of all, the question is to ask yourself, what are the anti-domains? What is anti-domain here? There is an anti-domain, so what kind of function is that? So you need to know the type of the function first. This is a polynomial function. It is a polynomial function. So we know that polynomial functions are defined everywhere. So domain of polynomials is all real numbers. Domain of polynomials is all real numbers. So if all real numbers is the domain of polynomials, there is no anti-domain. If there is no anti-domain, there is no point of discontinuities. Alright, so for polynomial functions, no point of discontinuity. Let's continue with an inverse function and a rational function. So what is the domain? So let's write the domain first. Domain is equal to all real numbers except what makes the function undefined. What makes the function undefined? What makes the denominator 0, right? What makes denominator 0? X minus 2 being 0, x being equal to 2. So r minus 2 is the domain. So your anti-domain is this excluded value 2. So your anti-domain number will be your point of discontinuity. Your point of discontinuity is this anti-domain number, because at that point you will have a break, right? You will have a vertical asymptote. Let's move on with another rational expression, rational function. So we still have a rational function for rationals. Remember what domain is. Your domain is all real numbers except what makes denominator 0. What makes denominator 0 is 1. So your anti-domain is 1. And if anti-domain is 1, then 1 is x equals 1 is point of discontinuity. So am I done? I'm not done. I got the point of discontinuity. What about the type of the point of discontinuity? What type of point of discontinuity do I have? I have 2 points of discontinuity: removable, non-removable. What kind do I have here? Let's check. If it is removable, limit should exist. If not, limit does not exist. So check limit at x equals 1. Limit as x approaches to 1 of x squared minus 1 over x minus 1. So when I insert 1 back, it's gonna be 0 over 0, which doesn't mean limit does not exist. Remember, it needs more work. So let's simplify the function then, or use L'Hopitas if you are familiar with that. So x squared minus 1 can be rewritten as x minus 1 times x plus 1 divided by x minus 1. X minus 1's will go. You'll have x plus 1 only. When you substitute 1 back, it's gonna be 1 plus 1, which is 2. So we have a limit. Limit exists. So since limit exists, we can say discontinuity is removable. So we can remove this discontinuity. We can fix this function. We can make this function continuous. How do I make this function continuous? Let me show you. So as in the rule, we're going to write the newly defined function by using piecewise function. So for the first condition, we are going to write the original function, which is x squared minus 1 over x minus 1. This is for x is not equal to 1 case. For x is equal to 1 condition, I am just going to write the value of the function. What is the value of the function? The value of the function is at 0, at 1, it is undefined. 0 over 0. At 1, 0 over... I can't write this. This is what I am going to do. I am going to redefine function so that it is continuous. So instead of writing the value of the function, if I write the value of the limit, if they are equal to each other, then they would be continuous. So let's write the value of the limit instead. What's the value of the limit at 1? We just found the value of limit at 1 as 2. So let's write 2 instead. So normally it was undefined. Now it becomes 2. Let me show you how it looks actually on the graph. Maybe it makes more sense. The function, when you simplify it, is the function x plus 1, right? X minus 1's cancel each other, x plus 1 remains. So this is how your graph look like. And there is a gap at what? At x equals 1. So here, somewhere here, there is supposed to be a gap, a hole. So this is what x squared minus 1 over x minus 1 function look like. It is not continuous normally. What I am doing by redefining the function is making this continuous by filling this gap. How do I fill this gap? Instead of f of 1 being undefined, I am writing f of 1 is equal to 2, because the value of the limit at that point is 2. If the value of the function at that point is also 2, it would be filled. If it is filled, then it is uninterrupted graph. If it is an uninterrupted graph, the function is continuous. So that's how I make the function continuous, by redefining the function, by writing this as piecewise function. For not equal condition, write the original function. For equal condition, write the value of the function. Alright? I think I forgot to do this for the previous question. Let me get back to the previous one. So this one, I found the point of discontinuity, but I didn't determine the type of discontinuity. What is the type of discontinuity here? To know, we should check the limit. Limit as x approaches to 2 of 1 over x minus 2. When I insert 2 back, it's going to be 1 over 0, which is undefined. So if limit is undefined, which means limit does not exist. If limit does not exist, then discontinuity is non-removable. So we can't redefine this function. It will stay as it is. It's an inverse function. If you want to picture it in your mind, it's something like that. So there's a break. There is no way that we can bring those two pieces together to make it continuous, make it uninterrupted graph. There is no way, there is no hole. We can only do this if there is a hole. Okay, so it is non-removable because limit does not exist. In other words, there is a break. We cannot bring those pieces together to make it connected to each other, to make this continuous. We can never do that. Okay, let's move on. Alright, next question. The similar type of question, this is a ministry question this time. And rational function is given. It says it's not continuous. This type is very common in ministry. It came 1, 2, 3, 4, 5, 6 times so far. So they like this type of question. It is easy and common. So the function is given. It says it's not continuous. So to be continuous, what should we do? What is the newly defined, redefined function? So as we did in this previous question, we are going to find the limit to write instead of the value of the function. When you check the options, if you see the first condition is all the same for all of the options. For not equal condition, you write the original function. Only the second condition is different. Equal condition is different. So we find equal condition by finding the limit. Okay, let's figure out the limit. Limit as x approaches to what? 3, right? 3 is the point of discontinuity. It's what makes denominator 0. What makes function undefined. So limit as x approaches to 3 of x squared minus 9 over x minus 3. When you substitute 3 back, you'll get 0 over 0 case, which means you rewrite the function. Limit as x approaches to 3 of x squared minus 3 factorized, x minus 3x plus 3. At the bottom, x minus 3, x minus 3's cancel each other. You will left with x plus 3. When you insert 3 back, 3 plus 3 makes 6. So this is the value of the function you are supposed to use as a value of the, this is the value of the limit that you are supposed to use it as the value of the function. So the second condition is supposed to be 6. So that's option A. Alright. So as in the previous question, let me show you how the graph looks like. So when you do simplification, the graph is x plus 3. It is something like that. And there is a gap at what? At 3. So your graph is supposed to have a hole at 3. This is a discontinuous function. There is a hole. And to make this hole filled, to fill this hole, I just need to redefine the function writing as a piecewise function so that the value of the function at this point is equal to the same as the value of the limit, which is 6. Okay, when I fill the graph is smooth. It is a continuous function. All right. So one more question about piecewise and two more actually. Let's do two more questions. So another type of piecewise question, you have less than or greater than condition. So for piecewise conditions, we should check those three conditions that we studied in the previous lesson. First condition, second, third. First condition is the value of the is the function defined at the breakpoint 0. Let's see. What is f of 0? F of 0 is equal to 2 times 0 minus 4 minus 4. It is defined, so first condition satisfied. Second condition, does limit exist? Let's check. If the limit exists, then limit from right, 0 from right, should be equal to limit as x approach to 0 from the left, right? What is left-sided limit? When you insert 0 back, 2 times 0 minus 4, which is minus 4. The right-sided limit, insert 0 back to the right, 0 to the left, 0 to the right. It is 0 plus 1, which is 1. So negative 4 is not equal to 1. Then we say limit does not exist. So limit does not exist. Right-sided limit is different than the left-sided limit. Then about the type of discontinuity, we can say f of x is discontinuous at x equals 0. For piecewise functions, we only focus on the breakpoint, the point that's given in the interval, okay? Not the others. So the function is only broken at these points. You don't care about the others. The function is continuous, smooth. At just this point, the function may be continuous, may be discontinuous. That's what we are checking. So the function is discontinuous at x equals 0. It's continuous everywhere else. Okay, it's continuous everywhere. Just that point is the point of discontinuity. So what type of point of discontinuity we have? Since limit does not exist, we have non-removable point of discontinuity. All right. Okay, there are many different same type of question in the book and the mystery. Try them. Okay, last question, last piecewise question. It is equal and not equal case. So the same applies. Since it's piecewise, we will check the if the function is defined, if the value of the function, if the limit exists. Is the function defined? The equal condition gives you the value of the function, if you remember. So f of 1 is equal to the equal condition, which is 0. So the first condition satisfies. Function is defined at 1. What about the value of the limit? We don't have two-sided limits. We don't have less than or greater than. So we don't have left-sided limit or right-sided limit. Limit is here. Not equal condition will give you the limit. So limit as x approaches to 1 of this function, 3x squared minus x minus 2 over x minus 1. So when I insert 1 back, I'm going to get 0 over 0. So by either using L'Hopital's or using simplification methods, we're going to solve this limit question. So let's do factorization here. 3x squared can be factorized as 3x and x, negative 2, 2 and 1. We are going to try one of them will be minus. 3x times 1, 3x, x times 2, 2x, and the middle term is negative, so 3x should take negative. If 3x is taking negative, then 1 will take negative. If you remember this factorization way, you factorize the first term as 3xx, factorize the last term as 2, negative 1 or negative 2, 1, we don't know. You multiply them across, 3x times negative 1, x times 2, so the sum should give you the middle term. So negative x, so that checks the factorization. My factorization is true. So I will write this as 3x plus 2 times x minus 1 equals 0. Of course, if you use L'Hopital's, it is much more easier. No need factoring and stuff. So I am not equalizing it to 0, sorry. So I just factor this. Let's use this. Let's rewrite this. Limit as x approaches to 1 of, instead of this, I'm going to write 3x plus 2 times x minus 1 all over x minus 1. X minus 1's will go. Put 1 back. It's gonna give you 3 times 1, 3 plus 2, 5. So you got the value. So limit exists. So second condition matches. So what is left? The last condition. Check the last condition. What was the last condition? The value of the limit being equal to the value of the function at 1. Are they equal to each other? What's the value of the function at 1? It was 0. What's the value of the limit at 1? It was 5. They are not equal to each other. The last condition didn't satisfy. Then, unfortunately, limit does not exist. Sorry, the function is not continuous. So, f of x is discontinuous. At what? At the given point. We don't look for the other point, just the given point. At the interval point, it is 1. The breakpoint is 1. F of x is discontinuous at x equals 1. So x equals 1 is point of discontinuity. The function is continuous everywhere else. Okay, so see, the first condition is satisfied, second condition is satisfied. So if the last condition did not satisfy, then it is not continuous. So all of the conditions should match if the function is continuous. One of them being not satisfied is not going to make the function continuous. So be careful, check all of the conditions for piecewise. So the function is discontinuous. What about the type of continuity? Discontinuity. Does the limit exist? Yes. So since limit exists, then function is, the discontinuity is removable. Discontinuity is removable. So if I remove the discontinuity, I can redefine the function. Let's redefine the function. How am I going to redefine the function? For not equal case, I'm going to write the given function, original function. What was the original function? 3x squared minus x over minus 2. 3x squared minus x minus 2 divided by x minus 1. For equal condition, instead of writing the value of the function, because it was making the function undefined, I am going to write, it was not making the function continuous. I am going to write the value of the limit, so that function is continuous. What was the value of the limit? The value of the limit we found in the second condition as 5. So instead of 0, we are writing 5. Alright, so your graph was something like that, and there was a gap at x equals 1, a hole at 1, and there was a point. The function was defined at 0. What did we do by redefining the function? Instead of writing the point here, we took this point, put it back to fill the gap. So our new function becomes, there was the gap, new function, the gap was filled, and no more point here. That point is shifted to this empty point. So our function, our graph becomes a smooth graph, continuous graph. All right. So we will continue with other types of question. That's all for now.